Hi crew, welcome back again to another tutorial video. This is Parfait, and today I'm going to show you how to do a nonlinear Riks analysis on ABAQUS. This is a second step continuing on from the previous tutorial video where we learned in the last video how to do an eigenvalue buckle analysis to basically approximate or calculate the elastic critical buckling, shear critical buckling capacity of a typical plate girder. So where we ended last time was somewhere like this, where we had our eigenvalue results. And from our eigenvalue, we looked at the first positive eigenmode to look at the V critical. And so our eigenvalue from last time was basically here, 199.23. And so in today's videos, we're going to do a nonlinear analysis. And for the nonlinear analysis, we do not do an eigenbuckle analysis. We actually do what is called a Riks analysis. So R-I-K-S, Riks. And this is a nonlinear analysis. And before I show you, just to speak a little bit about it, is that this analysis will take longer than the eigenvalue. It may take a couple of hours, depending on the size of your specimen, depending on the grid, the mesh, and all these other things. And it will also occupy a lot of space. So each output ODB file of the Riks analysis will be on the order of 1 to 10 gigabytes. And so let's start. So this is where we ended last time. And so in order to do a Riks analysis, so what we will do is, now you can see my ABAQUS screen. You go back to the model view. And in the model view, we have our model that we created here, which we called VCR buckle G6T1. And this came from the paper, the journal paper, this paper here, the post-buckling mechanics in slender steel plates under pure shear, a focus on boundary condition and load path. So in this paper, we did model this panel extension condition under pure shear using these boundary conditions. And the model that we use is this model here, G6T1. And here are the geometric and material properties for that model. And so today we're going to do a nonlinear to be able to calculate the VU, or the ultimate shear capacity. So let's go back to ABAQUS. On our ABAQUS, where we have the model, we will click on it. And once it is highlighted blue, we will right click, and then we will copy this model. And then for this model, we will rename it. We will call it now VU, which is the ultimate shear, and we'll call it Riks, so R-I-K-S. And we'll click OK. And so once now if you look, we have two models. We have the original model, which is the VCR, the eigenvalue analysis, and now we copy the same model and we call this new model the Riks. And so we're going to come in the VU Riks model and double click on that. After we double click on the Riks model, then we will go back to the properties. So now we can see that we are in our VU Riks models. And so the process to do a Riks analysis is very simple. It takes less than 10 minutes. And the main important things here are adding the plastic material properties. And so that's what we're going to do here. And since this was an experimental test, we have the records of the actual plastic material properties. And so how do we add plastic material properties? Similar in our model, on our property model, we come back to our material properties. And so what we're going to do, we're going to click on the material manager. You click on the material manager and a screen like this will pop up. And so this was our material property that we created, our steel with 210 gigapascal. We will edit this material property. So previously we had the density and the elasticity, where 210 gigapascal for the Young modulus and 0.2 for the Poisson ratio and 7850 for the mass density. And these units are in metrics. So the density here is in kilogram per meters cubed. So what we will do is add the plastic properties, and how we do that is we click on mechanical, come to plasticity, and we click onto plastic. And so now we have added the plastic material property, but now we need to add the actual values of the yield stress and the yield and the plastic strain. And what I usually also do here is I also add my temperature data. So I will check the box that says temperature, and all of our models, we run it based on ambient temperature. So standard typical temperature, 20 degrees Celsius. And so the material properties for this model from the experiments are right here in this table here. I have most of them here. And so G6T1, and we have these material properties here. And so what I will do is copy the yield, the plastic, and the temperature. Just the first 5 bucks, because we go from 0 strain to elastic to plastic. So we'll copy these values, and we will come back to ABAQUS. And we will paste these values. And so now we have our plastic properties. We have the yield stress, we have the plastic strain, and we have the temperature. And these values here, remember, they are in newtons per meter squared. And so you got to keep track of your unit for the yield stress. You got to keep track of your unit for the plastic strain, and the temperature here, we just use ambient temperature, 20 degrees Celsius. And so we'll click OK. And so now we've added our material properties. After we add our material properties, now remember, we will go to the, and when you click on it, you see that the plastic material properties are there. So we just click OK. And so after adding our material properties, now we will go to our step, and we will click on the step manager. And here we see that the previous step that we had was the static general step and the eigenvalue step. So now what we will do is we will add a Riks steps. And so we will create a new step, and we will call this step Riks. And we will click on the static general, and you will usually find the Riks analysis in the static general. So you have to make sure that when you on your procedure tab to select general, and then to highlight the eigenvalue so that you can add the Riks step after the eigenvalue. So that is an important thing. And so after you rename your model name Riks, make sure it's highlighted to the eigenvalue so it can be added past the eigenvalue. And then you come down here in your procedure, you select statics Riks, and you'll click continue. And it's going to ask you from description, you'll just call this Riks analysis. And you will go to the incrementation. So the incrementation is basically the number of maximum increments of how we're going to numerically resolve the analysis. And so usually we want a large number of integration in terms of the increment. So here we will say about 2,000 maximum increments. And for the arc length, these values, you can use these base values here, and they will always work in most of your analysis. And so for the arc length, for the initial, we're going to do 1 e to the minus 4. So that's 0.0001. And then for our minimum, we're going to do 1 minus e to the power of 10. And for our maximum, we're going to do 1 minus e to the power of 3. And also for our estimated arc length is going to be the same as the initial, which is 1 e to the minus 4. After you have set these values, then you click OK. And then now we've added the rig steps. And so after we've added the rig steps, the next thing that you will need to do is to come to your loads. And if you remember in the loads here, I'm just going to bring them back again. So remember in the load, our load was 787.402. So that was 1 kilonewton or 1,000 Newton divided by the web depth, which was 1.27 meters. And so this was a shell edge load. And so we're going to keep this load for our Riks analysis. But what we need to do is we need to copy this load and add it into the rig steps. And so the way you do that is you open the load manager and you can click on the first load, right, that we created, and we'll click copy. And it's going to give us this screen here. And under the same copy load, we can keep the same name. We can just rename this load 1 Riks. And now for the step, we need to change this step into a rig step that we added and click OK. And so now we see that we have a new load called load 1 Riks, and it has been added to the new step of the Riks. And we also need to copy load 2. So the load 1 and load 2 are just the vertical and horizontal shear edge load. And then same way, load 2, we're going to rename this to load 2 Riks. This will be Riks eigenvalue, click OK. And so now we've copied our load. The other thing that we need to do after copying our load is we need to double check that our boundary conditions have been propagated to the Riks. And so we will click on the boundary condition manager. And when we check on the rig steps, the boundary condition that we have assigned have been propagated to the rig steps. So your boundary conditions are good. And so after we've completed this, the next thing that we need to do now, since we're only running a Riks analysis, we will need to suppress the static general step and the eigenvalue step. And how do we suppress a step? The fastest way to do that is basically by looking at in this windows here. If you scroll down to your step manager, which is on this window right here, where you have step, if you click on the plus drop down, you will see all of your step. You have the initial, the static general, the eigenvalue, and the Riks. And so we will select the static general and hold the shift key, select also the eigenvalue step, right click, and then click suppress. And so once we suppress this step, we'll see that it puts an X sign on it. So what that means is that we can run an analysis with only the rig steps activated. And that's what we want. And we also have to double check that the nonlinear geometry is on, and it is on, so it is good. So after we've done that, the next thing we need to do now, since we've suppressed our static general eigenvalue step, we'll need to add a history output for the result and also a field output for the result. So to do that, in the module under the step, we will come here and create a field output, and we'll make sure it's in the rig steps. Continue. And then here you will just select the pre-selected default. And then under the pre-selected default, I also like to specify my shell output in terms of the integration point. So we can do 5 integration points. So on the surface, it will be 1. Since our analysis used 5 integration points, we'll do 1, 3 for the center of thickness, 5 for the surface of the other side. And so, and also here, I also like to output my section forces. So you will click on the drop down of force and reaction and select SF, the section forces that will, and the section moments that will allow us to calculate things like the actual membrane stresses and things like that. So we'll click OK. And then we also need to add the history output. So we'll click here on the history output, continue since it is risk. And then here it will just be the pre-selected default. as well, and then we click OK. Once you've added your history field outputs, then we will need to add data about information about the actual imperfection for the analysis, because if we do not add any imperfection to this model, the plates will not buckle. All plates numerically will need to have some form of imperfection in order to create the onset and push it to buckle and to actually go from elastic to plastic into its correct Riks analysis. And so, since this is a nonlinear analysis, the imperfection that we're going to put here are the previous imperfection that we calculated in our eigenmode step. And so if we now, what we will do is we will come back to the job module, and in the job module we have our VCR buckle. And so what we need to do is we need to copy this name, right? So we will click on, I usually click rename and just copy this, Control C, cancel here. And so we copy this name VCR buckle. And so when we look at our result, in our result from the eigenvalue, the first positive mode was the second eigenmode. And so this is important because what we're going to do is we're going to basically tell in the Riks analysis to use this buckle as the initial imperfection for the Riks analysis. And so if we now we will go back to our job, and we will need to now create our before we create our job, what I like to do is to put the information about the imperfection. So how we do that now, after we've copied our name, we will click on the View Riks model here, right click on it and click on Edit Keywords. And we wait for a second, and then it's going to give us this screen. And so in this screen, we can also double check that we have everything correctly. And we just go all the way down first, and we see it has the previous information from the eigenvalue analysis, this node phi u. What we need to do is we will need to delete this node phi u. So we'll just put our cursor there and erase the node phi u star. And we will now scroll all the way up and find our step, Riks steps. And in our step, Riks step, this is where we're going to, above that, this is where we're going to put the information about the imperfection. So how do we do that is we're going to click right above that, and you need to make sure that you have the 2 stars in front. And so we're going to type model, and we're going to type 1 star, and we're going to say imperfection. And this is very case sensitive, so make sure you do not type with errors on your on everything that you type in terms of the words. And so the imperfection is going to be equal to, now we need to put the actual name of the job from the eigenvalue analysis, and that name is the VCR buckle G61, and then comma, and we need to tell it at what step to take the job from. And if you remember, in our eigenvalue analysis, the eigenvalue analysis was the second step, because the initial step is step 0, the static general step is step 1, and the eigenvalue is step 2. So we'll say step equals 2. And then enter. And then now we need to specify the eigenmode. And so the first positive eigenmode in that VCR buckle result is the second eigenmode. So it will be 2. And then comma. And then now we need to put the scale of the imperfection, the scale of the initial imperfection. And so if you go back to the paper, in the paper, if you read through the paper, it specifies that for the imperfection of our model in our finite element, we use the imperfection of d over 1000. And so the imperfection of D over 1000, that just a scale, it's just a scale imperfection. So the depth of this plate was, and it's specified here. And so you see is that it says that the initial geometric imperfection magnitude of D over 1000 was used for the validation. And so what that means is that you will take the depth of your plate, so 1.27 meters, divide that by 1,000, and that gives you 0.00127. And so that is what we'll input as our scale imperfection of the eigenmode. And so we go back to ABAQUS. Next to the eigenmode that we input in the data keyword, we'll put 0.00127. And so after that, that is it. So you have your model, you have your imperfection, which is come from equal to the VCR buckle that we ran. We have the step, which is calling on the eigenvalue step, which is the second step, and the 2 represent the eigenmode, and the 0.00127 represent the scale of the imperfection. And then after that, you double check here that you have your incrementations, you have your loads are there, your field outputs are there, and your history output is there. And you can scroll up, you see that your boundary conditions are there, your plastic properties have been added, and then you will just click OK. And so once that is done, then we come back to the module on our job manager. We can click on our job manager and we can create a new job. And this job, we will call it VU Riks. And this is G6T-1, G6-T1. And then we click on, and then we have to make sure that on your source model, it selects the VU Riks model. Click OK, continue. And then here for description, we just call it, it is the Riks analysis of G6-T1. And then you can also put the imperfection value here to remind yourself. So we can say imperfection D over 1000. And then similar to here, we will come on our memory, decrease the memory to 60%, and then parallelize our model into 4 processors. So check the box and then increase the processor to 4. And then keep the precision as single precisions and everything else the same, and click OK. So now you've added everything. And so now after this is done, you're ready to submit your job for your analysis to run. Now, this will take a couple of hours, and you can run it and go do something else and come back when the job is done. So you can keep monitoring as well as we did last time. You can click on the monitor and then track the progress of your job. So you click on your Riks analysis, now you'll click submit, and then now you submitted your job. You need to make sure that you have enough space on your computer, and it's because it's going to run for a couple of hours. It depends on the size. Models like this usually will run for about 2.5 hours or so for it to complete the full analysis. So that's it for the Riks analysis on how to do a nonlinear analysis for bridge plate girders under pure shear load on ABAQUS. And I will upload these resources on the shared drive. Thank you.